Hi all. Let's continue with the floating point addition and subtraction operations. So in today's lecture, we are going to discuss about the steps of floating point addition and subtraction with the help of a flowchart. In floating point addition and subtraction operation, the two floating point operands are stored in two registers AC and BR. So the sum of the difference, if it is a addition operation, the sum, if it is a difference, if you are doing a subtraction operation, the difference of the particular two operands, it is stored in a AC register. So the algorithm of the floating point addition and subtraction is divided into four steps. The first step is check for zeros. The second step is aligning the mantissa part of your data. The third step is add or subtract the mantissas. And finally, you need to normalize the result. So this is your flowchart of floating point addition and subtraction. So it contains mainly the four steps checking for zeros. This part of your flowchart will describe you how to the first step check for zeros, and the second step is aligning the mantissa part of your data. You have to align the mantissa part of your data using the step align mantissa. So this part of your algorithm explains how to align the mantissa. And the third step is adding the mantissa, add or perform or subtract the mantissas, which is explained in this particular part of your algorithm. And finally, after you get your result, you need to normalize the result, and the process is said to be called as normalization. So this step of your flowchart will tell you about how to normalize a particular result. So your entire flowchart is comprised of the four steps. So if you understand each and every step in detail, you can easily understand this particular flowchart. Let's see in each step in detail. The first step of your algorithm is check for zeros. In case of check for zeros, you need to check if any of your operands are a zero. So that depends upon the result of your operation depends upon the operands which are stored in AC and BR registers. So before going with proceeding with the addition or the subtraction operation, you are first checking whether any of your operands are zero. If for example, if you consider AC and BR registers, which are your operands, if both the operands are zero, obviously the result of your addition or the subtraction operation becomes a zero. Similarly, if one of your operand is zero, the result of your addition operation will be the value of the other non-zero operand, right? Similar, so it depends the result which has to be stored in your AC register upon your values that are stored in your operands. So first we are going to check the values of AC and BR whether any of the operands are zero. So whether it is an addition or subtraction operation, we first start with checking the value of BR register. If BR register is not equals to 0, then it means it contains a non-zero value. Then again we check with the AC register. If AC register is a 0, in that case, whatever is the value of a BR register, that will be the contents of your destination register AC. So that is your result which has to be stored because AC is a 0. So whatever is the value of your BR register, that is your actual result. So next step is assigning the sign for your result. So it depends upon the type of operation that you are performing, whether it is an addition operation or a subtraction operation. If it is a case of an addition operation, then whatever is the result, the positive sign, this as it is the output of your addition operation. The sign bit will be the positive. But in case of subtraction operation, you have to complement the sign bit of the contents of AS flip flop. So it becomes so that it becomes a negative sign. AS will become negative, and whatever is the contents of BR, so that it becomes minus BR. Okay. So that is in case of a subtraction operation. So because we are performing a subtraction of AC minus BR, so the result should be minus BR. So that is how you perform. When BR value is a 0, then whatever is the contents of your AC, that itself is your result. So we are just we will end the process saying that it is AC contents of AC is the actual result. So in the other case, if BR and AC both contains a non-zero values, none of your operands are zero, both of them contains a non-zero value. In that case, we are going to proceed with the next step, which is aligning your mantissas. So the next step of your floating point addition and subtraction operations is aligning the mantissa part of your data. So for example, I have my registers AC and BR with this particular floating point numbers. Say AC contains 0.538123 into 10 to the power of 3, where my BR register holds a value of 0.123000 into 10 to the power of minus 1. So these are my two operands which are stored in AC and BR register. And this part of my data number is said to be called as a mantissa part 0.538123 and 0.123000. So in the next step, what you have to do is before implementing the addition or a subtraction on the mantissa part of your data, you have to align your floating point numbers in such a way that both the numbers have the equal exponents. So if you look at the exponent of AC, it is 3. If you look at the exponent of BR, it is minus 1. So when you want to add these two floating point numbers, your exponents should be the same. Then only you can proceed with the addition or a subtraction operation on these two numbers. So you have to align your mantissa part of your data in such a way that the exponents of both of your operands remains the same. So in which way you have to align the mantissa depends upon your flowchart. So here, this is your flowchart of aligning the mantissa part of your data. So the exponent of AC register is represented by small a, whereas the exponent of BR register is represented by small b. So in this case, we are going to first check the values of a and b, whether a is less than b or a is greater than b. If a value is less than b, the exponent of AC is less than the exponent of BR, then you need to perform alignment of mantissas in such a way that you have to perform a shift right operation on the contents of AC register and increment the exponent of A by 1. Okay, in this way you can align the mantissa. And if A is greater than B, then you have to perform a shift right operation on the contents of BR register and you have to increment the exponent of BR, which is B small b, by 1. So this is how you can align the mantissas. You are going. So if A and B both have the equal exponent, then you need not have to align the mantissa. You can directly go for the next step where you can add or subtract the mantissa part of your data. So if you look at this particular example, so the exponent of A is 3, the exponent which is stored in small b is minus 1. In this particular situation, A is greater than B, 3 is greater than minus 1. So when 3 is greater than A is greater than B, what you have to you are supposed to do? We are going to shift right the contents of B and increment the exponent of B by 1. So B is nothing but the BR register. So I'm going to perform a shift right operation. So shift right operation on the contents of BR register in such a way that I have to perform those many number of shifts so that the exponent of a BR register should be equal to the exponent of the AC register. So to make minus 1 to make minus 1 to 3, how many shifts I have to perform? Right shifts, I have to shift 4 times, 4 bits. So when I perform a shift right on this particular 4 times, it becomes 0.000011. So all these will be, it moves towards the right. So it becomes into 10 to the power of 3 minus 1. Since I am performing a right shift of 3, I have to increment the exponent by 4. So it becomes 3. So if you consider this situation, in this case there is no loss of data. Whatever data that you have, only there is only 1 bit loss of data. So if you look at this, after aligning the mantissas, the exponent of AC is 3 and the exponent of BR is 3. So you have aligned the mantissa part. So next we go for the next step where you need to perform an addition or a subtraction operation on the mantissa part of your data. So this is a flowchart for performing an addition and subtraction operations. So the performing addition and subtraction on the mantissa part of a floating numbers is same as performing an addition and subtraction operations on a sign magnitude data. So in case of a sign magnitude data, when you are performing an addition operation, you are going to first check the sign bits of first operand and second operand, AC and BR. AS represents the sign bit of AC and BS represents the sign bit of BR. You are going to perform an XOR operation on those two sign bits if the sign bit of XOR operation of the sign bits is a 0, then you are going to add the mantissa part of your AC and BR registers. And the result will be stored in E and A, where A contains the result, the sum of your addition of your mantissas, where E contains the carry flag, carry bit. So similarly, if the XOR operation of your sign bits, if it becomes 1, then you have to perform a subtraction operation on A minus B. So which is represented as A plus B complement plus 1, and the result is stored in EA. So similarly, when it comes to subtraction operation, again you have to perform an XOR operation on the sign bits of AS and BS. And if the result is 1, in this case it is the reverse. If the result is 1, you have to perform an addition of the mantissas. And if the result is 0, then you have to perform a subtraction operation from the mantissa part of your data. So this is similar to your how you perform the sign magnitude addition and subtraction operation. So consider this example where my first operand AC contains 0.532 into 10 to the power of 3 and the second operand BR contains 0.712 into 10 to the power of 3. In case of an addition operation, I am just performing an addition of just the mantissa part of the data. Exponents you need not do because you have already aligned the exponent and this will be the exponent of your result 10 to the power of 3. So you just perform an addition of the mantissa. 2 plus 2 4, 3 plus 1 is 4, 5 plus 7 is 12, where 1 is written as a carry here and 2 here. So this carry will come here. So it becomes 1.244 into 10 to the power of 3. In case of a subtraction operation, the same way you perform a subtraction only on the mantissa part of your data. So it becomes 1, 3 minus 2, 1, 5 by minus 5, 0. So it becomes 0.011 into 10 to the power of 3. So you're performing an addition operation on the mantissa part and subtraction operation. So and the resultant exponent will be into 10 to the power of 3 for both the cases. The next step of your floating point addition and subtraction is normalizing the result. So once you have done with your addition and subtraction operations, whatever result that you got out of them, that result might not be a normalized result. Whenever we perform any type of an operation in a floating point arithmetic, we have to ensure that the result is in a normalized form. In case of an addition operation, their overflow situation might occur due to the result. In case of a subtraction operation, there is a possibility of underflow. So what is an overflow and what is an underflow? So overflow is nothing but when you look at this particular bit before the point, this particular bit, if it contains a non-zero value, then we mean to say that the addition operation results in an overflow situation. The result of an addition is an overflow. So in order to normalize this result, you have to perform a shift right operation of the particular result and increment the exponent by 1. So when you perform a shift right on this result, it becomes 0 point. This 1 will take this MSB bit of the mantissa part. So it becomes 0.124 into 10 to the power of, you have, since you have shifted towards your right, you have to increment the exponent by 1. Since it is 1 bit, you have to increment the exponent by 1 bit. So it becomes 10 to the power of 4. So it becomes 0.124 into 10 to the power of 4. This is your normalized result in case of an addition operation. When it comes to a subtraction operation, so when your MSB bit of your mantissa, which is nothing but the A1 bit. So when you're, there is one more thing, when you're performing a subtraction operation on the two operands, if both the operands are equal, then there is a possibility that the subtraction may result in 0. The result will become 0. Or else, the other possibility is when you're performing a subtraction on two floating point numbers, there is a possibility of underflow. So whenever your result is 0, there is no problem. You will end the process taking the result into account. But whenever there is an overflow situation, if the result is not a 0, it is a non-zero value, then you have to check for an underflow situation. So what is an underflow? When your MSB bit of the mantissa part of your data of the particular result. So this is your result. The MSB bit of the mantissa is nothing but this particular bit after the point. This we call it as A1 bit. So mantissa is stored in a AC register. The result is stored in AC register, and that A1 bit is the most significant bit. It is represented by A1. So if this particular A1 bit contains a 0, then we mean to say that there is an underflow situation. So whenever there is an underflow situation due to the result of a subtraction, you have to perform a shift left operation on the result to get it into a normalized form. So you are going to perform a shift left so that your result becomes 0.110. I am shifting the 0 towards the left. So it becomes 0.110 into, when you are performing a shift left, you are decrementing the exponent. So it becomes into 10 to the power of 2. So this is how you have to normalize the result in case of an underflow situation in a subtraction operation. So the same thing is explained in this particular part of your flowchart. So you are performing an addition operation and your result is stored in EA, where A contains your sum and E contains your carry bit. So based on the carry bit, you are going to identify whether there is an overflow situation due to addition or not. If your carry bit E contains 1, it means there is an overflow. If E contains a 0, then we mean to say that there is no overflow. So whatever is stored, this is nothing but your E bit. If it contains 0, there is no overflow. If it contains 1, there is an overflow. And when there is an overflow, what we are doing, we are performing a shift right on the contents of A, which is nothing but AC, and the how then you're going to transfer E. How you are performing shift right, you're transferring E to A1. So if you look at this, whatever is in E, it is transferred to A1 bit, and then you're going to increment your exponent. This is how you're normalizing the result in case of a addition operation. When it comes to subtraction operation, after performing a subtraction operation, there is two possibilities. One, the result of your subtraction can be a 0, and the result of your subtraction can be a underflow situation. So that depends upon your carry flag E. So if E is a 1, E contains, the carry flag contains 1, then you are going to again look into the value of A. So which is your mantissa part of your data. If A is equal to 0, which means the result of your subtraction is 0. Here say you are subtracting 0.1 minus 0.1. It gives you a result of 0. So in that case, when your mantissa is 0, the result becomes 0. So AC becomes 0. So in that case, you need not have to normalize the result. And other situation, if E value is 0, based on your carry bit, if E contains a 0, now whatever is the value of your E, you have to give a complement sign. So which means the result is a negative value. So you have to perform a 2's complement of the contents of a AC register to get your actual result. So you are performing a 2's complement of the result and you are complementing the sign bit of your result. So that will give you my actual result. So A and AS now stores the 2's complement of my result as well as the 2's complement of the sign bit. Now you are going to check the underflow situation. So this underflow situation can be checked based on the MSB bit of your mantissa part, which is nothing but the A1 bit. If A1 bit is a 1, so this A1 bit, if it is a 1, then we mean to say the result is in a normalized form. So we end the process. If A1 is a 0, then it is an underflow situation. So we have to perform a shift left on the contents of AC register and decrement the exponent by 1. And this process has to be continued. This operation has to be continued until you get your A1 bit to 1. So you have to perform those many number of shift left operations until your A1 bit reaches 1. So that is how you normalize the result in case of an underflow situation. Once your A1 bit reaches 1, then you end the process. That will be your normalized result. So this is how you normalize the result with the help of your flowchart. So this is the overall flowchart of your floating point addition and subtraction, where this part will give you, will check for zeros. This part we are aligning the mantissas by checking at the exponents, and here you are going to perform an addition or a subtraction operation, which is just like your sign magnitude addition and subtraction. And once you get your result based on the values of E, which is stored in the flip flop, a carry bit, which is stored in a E flip flop, we're going to check whether it is an underflow in case of a subtraction or an overflow in case of an addition. If at all an underflow or overflow situation occurs, we are performing a normalization step to normalize your result. So this is the overall flowchart of floating point addition and subtraction. So if the first step is check for zeros. If BR value is 0, the operation will be terminated because whatever value is in AC, that is your actual result. If AC value is 0, we are going to transfer the BR into AC because whatever is the value of BR, that is will be your result, and we are going to complement the sign if it is a subtraction operation. If it is an addition operation, the whatever is the positive sign, that will be a sign of your result. But in case of a subtraction operation, so if 0 minus BR, the result should be minus BR. So you have to complement the sign bit to minus. So if both the operands, none of your operand is a 0, then we proceed with the next step, which is aligning the mantissa part. In aligning the mantissa, the magnitude comparator is attached to an exponents A and B. So if the two exponents are equal, we perform the next step, which is adding the mantissa part of your data. But if the exponents are not equal, small a and small b, then the mantissa, which is having the smaller exponent, it is shifted to the right and exponent getting incremented. So this process of shifting has to be repeated until the two exponents are equal. So that is your aligning the mantissas. You have to align your mantissas in such a, of your operands in such a way that both of your operands exponents remains the same. So next step is addition and subtraction of the two mantissas. So in this step, you are going to perform an addition and subtraction operations on two mantissas, which is identical to floating point or a fixed point addition and subtraction algorithm. So the magnitude part of your data is added or subtracted depending upon the operation and the signs of the two mantissas. So if an overflow occurs in case of an addition, when magnitudes are added, it is transferred to the E flip-flop, which is a carry bit. If E bit is equal to 1, then how you're going to normalize? You're going to transfer the bit into A1, and all other bits of A are also shifted to the right and exponent must be incremented. So that is how you normalize the result in case of an addition operation. When in case of a subtraction operation, if the magnitudes were subtracted, the result can be either a 0 or it can lead to an underflow situation. If the result is a 0, the entire floating point number, the result AC is made as 0. Okay. But if there is an if the result is a non-zero value and there is an overflow underflow situation in case of a subtraction, that is identified by the A1 bit of your mantissa if it is a 0. If A1 is 0, it means there is an underflow situation in your result. So in that case, the mantissa has to be shifted towards the left and the exponent has to be decremented, and this process has to be repeated. The A1 bit has to be kept on checking again and again until A1 bit remains 1. So you are going to perform this normalization until your result comes to a normalized form. How do you check that? Based on the A1 bit. When A1 bit is equal to 1, the mantissa is said to be in the result or a mantissa is said to be in a normalized form, and you are going to complete your operation. So this is how you are going to normalize the result in case of addition and subtraction operations, which is your last step of your floating point addition and subtraction. Thank you.